Well, hello. My name is Jason McCrossy. I'm part of the Goldschlager team. And that's my team name, guys, up there. And we're going to talk about proportional controller today. Not about the sign or relay or any stuff like that, because no one really pays attention to that. But basically, this is what I'm talking about. Steady-state operating curve. It's what I'm going to point out to you so you can describe my results and why. I'm going to talk about that. Root locus, how we came up with the results. Proportional controller, we can talk a little bit about that. And so on and so forth. As you can see, this is, as you can't see,
you can point out this. Point out this.
Steady-state operating curve. And it's relatively the same slope all the way through. Same on this side too. And our results for that, we got an average gain of 1.5 volts per percent. This is very, very important. And also, the output of the voltage system depends on the effect of the strips. Here's a root locus plot, just from 85% to 88%. Should have changed that to volts, but sorry. Anyways, next one. This is how we, this is why I have to talk about this, because I don't have too much time for this. We found our 150th, 110th, 1/4, and ultimate at these different angles. Now, here's some results for just the proportional controller. I will show this and all this stuff too. This is yeah, I'm going to skip this. Can I keep skipping?
Sure.
I have a point. These are different for proportional intervals. So we're changing the K value. You can see as it gets more monotonic quicker, so on and so forth. And we have all these results. And we're comparing ultimate gain and ultimate frequency. Now, this is the important part. Proportional integral controller. Dum, dum, dum. Here's our values that we came up using the root locus plot, which I was describing earlier. These are each value for each of our range, 75, 80, 80, 85, and so on and so forth. Now, this thing we should point out is they all look relatively the same, plus or minus a few points, something. Same thing basically throughout. So, this is compared to the proportional controller, 0.9, 0.3, 0.1. 0.9 is for your ultimate. We are around there. 0.3, we're a little higher, but this is just the approximation found by the root locus, and 0.1 for crystals. This is a graph of windup. I don't know if I'm doing this right, but I think it's when this area equals this area. Sounds good, and then the input changes so the output matches the set point. And that's just for you guys to see. Oh yeah. Now we're going to talk about the results for our ultimate KC. Please don't do that again. Alright, for our ultimate, I'm going to just show you guys about the 90-95 volt range because our K is 1.5 basically throughout. So we're just going to focus in on this area right here instead of everybody's. Also because when you try to do everybody's on Excel and try to change graphs, your computer crashes over and over again. So we're just going to talk about this for 90-95. But anyways, for 0.4 for our tau sub I, we have a K of 1%. Gives you a very, very ultimate looking graph. Okay, so C and so tau sub I. Tau should be tau sub I. Because that's you know. Hey, change your down. Anyways, 0.2, and KC is 1.3. Still got this crazy look going on. Same with this, 0.7 and 1.4. So let's move on to the 1/500th decay. Now these are just results using the values of the root locus that we found. So far, so good. Kind of decaying. I don't know if you call that 1/500th, but just judging anyways. This probably isn't a 1/500th decay, but this is just a result of what we found using the root locus approximations. And same thing with this. Now, this is where we're going to get a little interesting. When you use the KC, the criticals. This looks pretty critical to me, I would say. Would you say? Indeed. We're starting here, we change the set point, and it takes about 31 seconds to get to the steady state.
No, it doesn't.
No, it doesn't. I mean, 1 second.
Thank you.
You're right. We'll talk about that a little bit more. This, using 0.2, you get a KC of 0.1. Relatively long time to reach set point, 3 seconds. And this is a 0.7 calcified with KC of 0.2. It takes a lot longer, about 5 seconds. Now, let's explore this 0.2 KC critical some more. Comparing it to our KC 0.1 using the root locus approximation, I thought that time is a little long, maybe over-damped, right? Over-damped. So, I changed the KC, increased it a little bit, and we're still over-damped a little bit. We changed the time that it takes to get to the set point, 2 seconds instead of 3 seconds. Let's keep going. All right. Now, changing the KC a little bit more to get to 1 second, maybe 1.5. But I want you guys to see this little bump. Watch this. Boom! It's bigger. Yeah, that's cool. Anyways, that also changes the depth, or the time it takes to reach the set point to 1 second. I like to call this the thing. We pointed this out earlier in our other presentations, but now I'm kind of wondering what that is. This is why it's kind of different than other type of presentation if you ever saw it. Let's explore it. Here it is at here's the thing. At 0.2 seconds with a KC of 0.4. This is our critical response that we would say we would recommend if we were using a calcified of 0.2. Here's our calcified 0.04. It's a lower calcified. It still takes 1 second to reach that point, but it's the same. Interesting. Let me show it over here. There's no thing. And that was kind of cool, so I had to show that to you guys. Now, we're concluding here that the proportional integral controller has no offset. It uses 2 tuning parameters, but it does have a case of a wind up, wind down that you would have to take account of. The root locus modeling is good for approximation, but will not give you the exact values unless you use some hardcore modeling and get pretty accurate. But it's just a model, so further testing is required to find your better parameter. And for a critical response, I recommend that you use, or we as Goldschlager recommend, use a calcified reload of 0.04 seconds with a KC of 0.1. This will give you a quick response, but won't have the thing. Any questions?
This girl, see?